Hello everyone, welcome back. Let's deal with Physics 209, Calc-based physics, and let me show you Chapter 16 from the Katz book. Let me talk about problems 45, 46, 74, 77, 80, and 81. Again, people looking at this outside of the calc-based physics can probably get a lot out of it as well if they have the textbook, because much of the material that you do, much of the time you're not doing calculus. Sometimes you are, of course. It's calc-based physics, but sometimes you're not. So always it's always an option, even for the non-calc-based physics classes. If you have access to the book, you should be okay for being able to get something out of it, certainly. For problem number 45. Problem number 45 from the Katz, problem number 45 from chapter 16 from the Katz book says the following. A block of mass m equals 1.23 kilograms is attached to the end of a spring with a spring constant 565 newtons per meter. The block rests on a frictionless surface, is pulled to the right, and is held there. When released, the block undergoes simple harmonic motion. There is A and B on this one. A, if the maximum speed of the block is 7.12 meters per second, what is the amplitude of the motion? B, what is the speed of the block when it is halfway between the equilibrium position and the maximum displacement? So basically we're talking about a spring system here, guys. And so let's just figure out where we want to go and how we want to do it. Should be pretty basic stuff. M is 1.23 kilograms. That's the mass. M is 1.23 kilograms. The spring constant K is 565 newtons per meter. The maximum speed of the block is going to go right through the equilibrium position, and that's going to be 7.12 meters per second. Let's see what else we have here. They want to know what is the speed of the block when it is between the equilibrium point and the maximum displacement. The maximum displacement is A, so half of A is going to be the x under consideration that you're going to be looking at for problem B. Okay, before we get there, let's consider this, and let's consider these guys right here. So we've got some data here. So to do A and B for this should be okay for us. There's a lot here, guys. I wrote a lot of notes on this one in Canvas. All of this should be in Canvas, and you might have, some people might have the preference of not, of going through whatever is written down at their own pace and not looking at what's being written on the blackboard and talked about live or semi-live, right, on film. That's your choice, okay? But anyway, there's a lot here, and they talk about a number of things. So let's see what we can say. I said a whole bunch already which is in my notes in Canvas, but I also did it live, so I'm not going to repeat that. I'm just going to come back to a number of things I guess you could say. We'll say this. We'll say that omega is equal to the square root of the quantity K over M, or M is mass. Omega is going to equal the square root of the ratio 565 divided by 1.23. I bypassed the units because all the units agree. All the units are MKS system of units, so you're going to be okay. It's not going to be an issue. When you do that, nobody really asked you this, but if they did, I guess you could say a whole bunch of things. The angular frequency, that's not the frequency f, it's 2 pi f. 2 pi f, the angular frequency, is this. So, nobody really asked us that. what is the amplitude of the mode? They asked us for the amplitude. Well, the amplitude should be pretty good, pretty straightforward. Is it true that V max equals omega times A? Yeah, omega times A times the sine of something. I want the sine to be a maximum. If it's times the cosine, then I want the cosine to be a maximum. Cosine or sine have maximum at the number 1. 1 times omega A is omega A. If it's at a maximum, remember now, the way it usually works out is you're talking about omega A, whatever that may be, right? I mean, it could be the way it gets written. In terms of magnitude, it's looking something like this. Well, if that's a maximum at 1, the maximum you can have here is just omega A. So omega A is going to be indicative of V max. What's A going to be? A is, A is going to be V max divided by omega. Well, let's go. Let's just plug the stuff in as we know it. The V max is 7.12. Omega is 21.43. You're going to grind this out and you're going to be there. You're going to simply get the answer that way. So for A, part A on this, it's going to be 0.332 meters. 0.332 meters is what the amplitude is going to be. And it would have been nice if I'd have written that, right? Equals the amplitude. So amplitude is 332 meters. And there you go. That's the most formal way to write it, I guess you could say. .332 meters is what that is. That's A. B, they're essentially saying how fast is it going when it's how fast is it going when it's here? When x is equal to 1/2 A. Well, look, guys, there's, I guess, a number of ways you can play this whole thing. I'll just say it this way. For B, energy is conserved. So the maximum energy, there's a whole bunch of ways you could say this. E is equal, EI equals EF equals sum E, and that's, sum E is the total energy of the system. The total energy of the system is the kinetic energy of the system plus the potential energy of the system. Well, there are times when it's all potential energy, no kinetic energy, when it's at the outskirts. When it's going right through the middle, it's all kinetic energy and no potential energy. So either one of these works. You could take 1/2 m V max squared. That's when it's going right through the middle. It's all kinetic energy, no potential energy. This guy right here will indeed be equal to this. The maximum kinetic energy is everything. The PE is 0. Or the maximum potential energy means no kinetic energy. Either one makes it work. So either you can use either one of these, and I know what the amplitude is. I can square it. I know what K is. I know what 1/2 is. I know what V max is. I know what M is. I know what that is. It should work. It will work. Okay. It's not an issue. I can use one or the other. I think the way I had gone about it was, and I said there's so many ways to go here. Your best way to go is probably use this one, because they gave you the data that x is equal to 1/2 A. And they want to know how fast it is when x equals 1/2 A. Tell you what I'm going to do. 1/2 K A squared is the entire energy of the whole system, because it's all potential energy, no kinetic energy present. Maximum kinetic energy is the energy of the whole system, or maximum potential energy is the energy of the whole system. They're equal to each other. they're kind of split up. If you don't hit the extremes, you got to like add them together. You got to say, well, wait a minute. There's 1/2 mass v squared when the thing happens to be at 1/2 a plus 1/2 kx squared. Well, we already know that, see, 1/2 kx squared, we already know that the x is 1/2 a. Okay, sounds pretty good to me. Let's see what I can do. 1/2 ka squared, 1/2 mv squared. There's these halves all over the place, guys. There's a half here. You square this. There's a quarter here, and there's a squared here. Tell you what I'm going to do. Let me multiply by 2. Well, we can do a whole bunch of stuff here, I guess you could say. Let me multiply by 2 all the way across, just to make the mathematics a little easier to look at. Do you have to do that? No, you don't have to do anything. The only obligation you have when you're doing these problems is to solve the problems. The half is gone, the 1/4 is here. I'll just bring the 1/4 out of here. And I got to here. I'm certainly not done, but I am there. So, we got what A was. Keep working with B. Let's take that thing way down there. Way down to the far right, lower far right. Let me try to solve for V squared. Let me subtract 1/4 Ka squared on each side. So I got Ka squared minus 1/4 Ka squared equals mv squared. This is 1. 1 Ka squared minus 1/4 Ka squared is 3/4 Ka squared equals mv squared. Interesting, interesting. And a whole bunch of levels here, I guess you could say. Let's divide by m on each side. I'm purposely emphasizing what's going on there. Why don't you square root both sides? The V is going to be the square root of all this. Going on here? Well, I see a lot of stuff here. You can kind of cut to the chase pretty easily here. You plug in A, square it. You take a K, put it in there. Here's M, put it in there. K divided by M, get an answer. Take A squared, get an answer. Multiply by 3/4, get an answer from all of that. Square root it, you got V. It's that simple. It's that simple. Now, see what we can say. I will say, maybe there's some interesting stuff you can, I guess, say here. Tell me how you feel about this. You would say here, square root these individually. You got the square root of 3/4 times the square root of K over M times the square root of A squared, which is A. Wait a minute. The square root of K over M is omega. That's omega A. The square root of 3 divided by the square root of 4, that's the square root of 3 over 2. That's V. Interesting, interesting. Omega A is V max. V equals the square root of 3 over 2 times V max. V max is 7.12. 7.12 times the square root of 3 over 2. Square root of 3 over 2 is the same as the cosine of 30 degrees, same as the sine of 60 degrees. It's about 0.86. 0.86 times 0.86 times 7.12. Anyway, it's of interest how the whole thing plays out, indeed. B, the V there at the end of the song and dance, you guys, square root of 3 divided by 2 times V max is 6.17. And that's B. That's 45B. Let's look at 46. Uh, 46 is closely tied up with 45. In problem number 45, the block's maximum speed. In problem number 45, the block's maximum speed is 7.12 meters per second. There is an instant in the motion when the potential energy of the system is equal to the kinetic energy of the block. Basically, they're trying to say the potential energy and kinetic energy are equally divided between one another. They both add up to the original energy. At what position next does this situation occur? Okay, pretty straightforward. So what's going on? Well, we said you could play this a bunch of ways, guys. You could say, I mean, there's a lot you could say, actually, but you can definitely say that the total energy is one or the other. It is 1/2 m Vmax squared or 1/2 Ka squared, A being the amplitude. Let's take it that way and find out the position where it's at. It is the total energy under consideration for 46 is 1/2 Ka squared. 1/2 Ka squared. What happens is, that's the total energy under consideration. It's 1/2 m Vmax squared, which is the same as 1/2 Ka squared. I chose 1/2 Ka squared because I want to get a relationship between what position does half the potential energy of the maximum occur. At what position does the potential energy half the maximum occur? We do know, generally speaking, 1/2 mv squared equals 1/2 kx squared. Sounds good to me. They just said, now we got it in the back of our mind, guys, there is a place where 1/2 mv squared equals 1/2 kx squared. They're both equal to each other. It's equally distributed between The kinetic energy and the potential energy are equal. At that point, this guy right here can be written as 1/2 kx squared. That's this guy. It's the same thing. And this guy indeed is still 1/2 kx squared. And that's going to equal 1/2 Ka squared. There's a number of ways to go here, guys. Let's deal with it a number of ways. Let me add 1/2 kx squared and 1/2 kx squared and get kx squared. Let me divide by k on each side. So it's really the key to the whole thing, guys. You get down to here, you're in business. If you square root both sides, you get x equals plus or minus a divided by the square root of 2. We already said that a was 0.32. We already said that a was 0.332 meters. Divided by the square root of 2 is going to get you there. X is equal to plus or minus. It's going to be on either side of the equilibrium position, ladies and gentlemen. This does matter. It's going to be plus or minus 0.235 meters. That will end the matter. And that's 46. Let's go to 74 and then 77. Let me just... Okay, guys, for 74, has A, B, C, D. Let's see what they got here. The total energy of a simple harmonic oscillator with amplitude 3 centimeters is 0.500 joules. A, what is the kinetic energy of the system with the position of the oscillator is 0.750 centimeters. B, what is the potential energy of the system at this position? So we want the kinetic energy and the potential energy. Well, if I add the kinetic energy and potential energy, I get the total energy. If I know what the kinetic energy is, all I have to do is subtract it from the 0.5 joules. 0.5 joules minus the kinetic energy is going to give me the potential energy. So A and B should go pretty smoothly. C, what is the position for which the potential energy of the system is equal to the kinetic energy? We pretty much went there. We're going to use this. Believe it or not, we're going to use that. Why? Because up here, we determined that this guy and these two guys were equal to each other. We played the game, we did the mathematics, we got to here. We're using this. We find the amplitude, we're going to divide the amplitude by the square root of 2, and we're done. And that's for, for 74. What is the position? C, what is the position for which the potential energy of the system is equal to its kinetic energy? We're going to find that place. D, for a simple harmonic oscillator, what if any, what if any are the positions for which the kinetic energy of the system exceeds the maximum potential energy of the system? Explain your answer. The maximum kinetic energy of the system is as much kinetic energy as the system can possibly have. The reason for that is all of the energy of the system will go into the kinetic energy. All of the energy of the system going solely to kinetic energy will give you the maximum kinetic energy, and there's no more energy of the system to be given up. There is no potential energy beyond that. So they're saying here, for a simple harmonic oscillator, what, if any, are the positions for which the kinetic energy of the system exceeds the maximum potential energy of the system? No, I mean the maximum potential, well, let me put it another way than I just said it. The maximum kinetic energy of the system is the entire energy of the system, because there's no potential energy when the kinetic energy is at a max. That maximum kinetic energy is equal to the maximum potential energy, because the maximum potential energy is the maximum amount of potential energy, and there's no kinetic energy present. Maximum potential energy equals maximum kinetic energy, but they never happen at the same time. Maximum potential energy means no kinetic energy present. It's all potential energy. And maximum kinetic energy means no potential energy present, because it's all kinetic energy. So I can answer D right now. For a simple harmonic oscillator, what if any are the positions for which the kinetic energy of the system exceeds the maximum potential energy system? No, I just explained that answer. D's already explained. Let's look at 74 and see what they want to say about it. There's a number of ways to do it. I did it, and I also showed it a number of ways. Could have just as easily used a lot of other stuff earlier. Let's. You can argue this a whole bunch of ways, guys. Let's just see what we can say about it. We'll kind of take it from there. All right, well, let's see what they say here, guys. Given the stuff they said about the oscillator, I mean, we'll say a few things, I guess, and ourselves, and we'll kind of take it from there in our approach here. We know that PE max is as much as you can have, and that's equal to KE max, and they never happen at the same time. In fact, the total energy of the system is always a constant. That right there. The total energy of the system is always a constant, and it's equal to PE max, or it's equal to KE max, because they're both equal. That's the total energy of the system. That's for sure. And that's this. And from there, you can tinker with this a bit, and you should be okay. Potential energy plus kinetic energy equals the total energy of the system. We already said that E was equal to this. They're telling us A, and that's the Y max, you guys, is 3 centimeters. Probably got to go here and say 0.03 meters. You got to go here. You got to go here, because everybody's working with the MKS system of units. 0.5 joules, 0.03 meters. Well, there's a lot here. I mean, what they're asking here, what is the kinetic energy of the system when the position of the oscillator is at 0.750 centimeters? So, a whole lot of ways I guess you could do it. The way I did it, I don't, now I look at it, I'm not thrilled the way I did it, though it's fine. I think it's a pretty clever way to do it. Let's kind of look at it, guys. The total energy of a simple harmonic oscillator with amplitude 3 centimeters is 0.50 joules. 0.500 joules. What is the kinetic energy of the system when the position of the oscillator is 0.750 centimeters. So the kinetic energy of the oscillator, huh? Well, I'll tell you what I'm going to do. Why don't I find the potential energy of the oscillator, and then I'll get it out of there. I'll take it out of there. So then I can find the potential. So I guess I'll find B first. How about we say this? 1/2 k y squared divided by 1/2 k y max squared, and that's the amplitude. That ratio, well, what is 1/2 k y max squared? What is that? It's 0.5. So 0.5 is the same as this on the bottom. And the top, we don't know what it is. We'll call it P for potential energy. 1/2 k and 1/2 k are out of there. This is not a bad way to go. It's not an obvious way to go as far as I'm concerned. I did this problem a while ago, and I got to look at it again just to kind of, is that for real? Yeah, it works. It certainly works. P over 0.5. Why don't you multiply by 0.5 on each side, and P is equal to 0.5 times y squared over y max squared. Here you don't have to change the units, because the units, as long as they're proportional to one, as long as the measuring sticks are the same, they're going to cancel out. You can argue that a bunch. We can all argue that a bunch of ways, I guess. But you can here, if it's a ratio and the units are all in agreement, it doesn't matter. It works just fine. This is easier done than said. Let's just do it. I want that ratio. They're making the claim 0.75 centimeters. The other one's 3 centimeters down here. That's the Y max down here. And then you're going to square that. And then you're going to square that. Interesting. That's 3 over 4. This is 3. 0.75 is 3/4. 3/4 divided by 3 is 1/4. 1/4 squared is 1/16. Half of 1/16 is 1/32. 1/32 joules. We just answered B. And I'll get more into that in a second. See exactly how you want to do this. You want to do, you basically got a quarter of 0.125. A quarter of that is there's probably a number of ways you can do that. Quarter of that would be 0.31667. So we'll get to that in a second here. Let's just talk a little bit. In these circumstances, what's going on? I'm going to answer A and B. Together, they got to add up to 0.5. So half of that is that, and the other, to do that one, to get you that one, would be 15 over, guys, look, what's 1/32 plus 15 30-seconds? That's 16 30-seconds. That's 0.5. Those are the joules. Those are the joules. So the potential energy at that point is 1/32 joules. The kinetic energy is 15 30-second joules. So let's see what we got here. We got A is 15 30-seconds joules, and I'll write that a different way in a bit. And the other one is 1/32 joules for the potential energy at that point. That's equal to the kinetic energy. And that's 0.46 0.875 joules. The other one is going to be the PE at that point, which is going to be 0.03125. Okay, I think I was off on that one, guys. When I did this one, a quarter of that. Correct. This is right. This is correct. So that's it. So there's the kinetic energy and there's the potential energy. That's the KE. It's that, which is this. That's the potential energy, which is this. Okay? True. You could have found what K was. If you wheel and deal with the mathematics, you guys, you could have come, I mean, I don't want to say this. I mean, you could have come back here. Nobody's really asking us this. So if not asking us, you know, who cares, you know. But you got 0.5 is the max energy. And you got 1/2 K Y max squared. 1/2 K Y max squared is 0.5. Do all the algebra that you got to do. What is it? Well, what do you say you multiply by 2 on each side? Divide by y max squared. K equals 1 divided by y max squared. That'll give me K to find the constant, the spring constant. If you do it, nobody asked you this. What the heck? We entered the dance. Let's go. Let's deal with it. That's 1,100. That's 1,111. 1,111.11. Nobody asked me, but there it is. I guess they're asking a question. I could use that to get everything out, to get a lot of answers here. C is simply saying, what is the position for which the potential energy of the system is equal to its kinetic energy? I tell you what, guys, I showed it I showed it differently in my notes. Please read them. That's another way to look at it. No harm with knowing a lot of different ways to do something, guys. The more athletic you are in these manipulations, the more versatility that you have in these manipulations, the less chance you're going to make a mistake, and there's more chance you can catch any mistake that you might make. We all make mistakes. You got a better chance to catch it the more you're training yourself with this stuff, the more versatility that you have doing this. Tell you what I said here. I got what K was through the song and dance here. I didn't have to do that. We did it. Let me kind of diverge a little bit from my notes and just say, hey, look, man, why don't we just make this a little easier to look at and just say this? Are you willing to say, now let's see here. They're talking on this one. What is the position for which the potential energy of the system is equal to its kinetic energy? So I'm not even, that's actual, I think what I might have given here, what is the position for which the potential energy of the system is equal to its kinetic energy? It's right between the two. Yeah, I guess that's true. Yeah, that makes sense, but I'm not going to show that. I'm going to do what I did earlier, guys. I'm just going to say that place is going to be A over the square root of 2, and it's going to be plus or minus. If that looks familiar, it should. Within the last half hour to an hour, we just did this. Okay, If that looks familiar, it should. Okay, so Y equals plus or minus A divided by the square root of 2. What do we got? Well, we got 3 divided by the square root of 2 plus or minus. And I'm getting 2.12. Just in case something crazy happens, guys, I guess it's good to catch things while you're doing them, I guess. We should be getting about 2.12 on that one. I think we are. I'm just kind of... About 2.12, that's what it was, yeah. And that's why I had determined. There's another way you could have determined it. There's always another way to determine this stuff, you guys. What are they saying here? Name a position. I'll name both places where that can happen. What is the position for which that can happen? It's plus or minus. I think I just gave one here. But, yeah, it can be location plus or minus 2.12 centimeters. Or what is that equivalent to? Well, we all know what it's equivalent to. And that's it. That's what Y is for that particular situation. D, is it possible to have that happen? What are the positions for which the kinetic energy of the system exceeds the maximum potential energy? The maximum potential energy is equal to the total energy of the system, is equal to the maximum kinetic energy of the system. The maximum potential energy can go into the maximum kinetic energy, can be converted to the maximum kinetic energy, but no more than that. Therefore, neither Pmax nor Kmax can exceed the other. No such point exists, as I was saying last time. Okay, that'd be D. Okay. That was 74, you guys. Let's go to 77. It is a little convoluted look to it, but we're going to be okay. A lightweight spring with mass so let me read it out. We'll kind of take it from there. A lightweight spring with spring constant K equals 225 newtons per meter is attached to a block of mass M1, 4.50 kilograms on a frictionless horizontal table. The block spring system is initially in the equilibrium configuration. A second block of mass M2 equals 3 kilograms is then pushed against the first block, compressing the spring by 15 centimeters. When the force of the second block is removed, the spring pushes both blocks to the right. The block M2 loses contact with the spring block 1 system when the blocks reach the equilibrium configuration. A and B, what is the subsequent speed? When it gets launched, what is the speed of block 2? B, compare the speed of block 1 when it again passes through the equilibrium position with the speed of block 2 found in part A. So it's A and B. 77 is a great question. So two things are, there's a block, the block's attached, bam, it's put together a bit, and we see some of the stuff that happens. Let me just see exactly how we want to quarterback, how we're going to do this whole thing, you guys. I think it's pretty decent, pretty straightforward stuff. Okay, so let me erase some of that stuff, and let's put some stuff up there and talk a little bit and see what the behavior of this entire circumstance amounts to. Okay. See how I want to do this. You're saying for 77, you guys. There's this frictionless environment now. It's, equilibrium position right now. It's going to get, so here's, this guy's M1. The other guy is M2. And what's going to happen is you are going to you ended up, what you ended up doing is, this guy used to be right here, and he's going to end up right here again. And the other guy is going to be flying off. And so this guy ended up getting compressed. He used to be right here. He used to be right here. He used to be right here, and he got moved over there. So its center was right here. His center was right here, and his center got moved over there. So how far did center get moved? He got compressed that way, X amount by M2. Here, you compress him, and then you let it go, and then bam, he goes flying. And there's where this guy goes flying. That way. And this is the equilibrium position again. No stretch, no compression. Right there is equilibrium. Here it's all compression. That's about what's going on. And then they're asking, what is the subsequent speed of block 2? Block 2 gets fired right off of there. He gets fired right off of there. How fast is he going? That's A. How fast is block 2 going when he gets fired off? That's V. V for velocity or magnitude of velocity. B, compare the speed of block 2 when it again passes through the equilibrium position with the speed of block 2 in there. So there's a lot going on here, guys. So let me try to make this make some sense. All right, guys, let's see what we can say about this whole thing. Well, there's a lot happening. There's energy going to be released, and from there I'm going to take all the considerations into account. Not really a collision here, but let us definitely say a few things if we can. They're telling us K is 225 newtons per meter. M1 is 0.450 kilograms. M2 is 3.00 kilograms. Delta X, the amount of displacement, I'll call it X. X equals 15 centimeters. The compression. That's 0.15 meters. 0.15 meters or 15 centimeters. This is probably the better way to go because they're giving us kilograms and everything else. And that's the same as that. And here are these guys. So we've got a number of things going on here, guys. We know for A, total energy of the system is equal to the initial energy of the system is equal to the final energy of the system. It's a frictionless environment, nothing's lost. It's a closed system, frictionless environment, bam. Thing fires off, the energy considerations, if we're careful, everything's fine. Energy initial equals energy final. We take it from there. Tell you what I'm going to do. E total is E. How about, since they're horizontal, they're not hanging, or you didn't climb up a building or anything, hanging, they're just there on that frictionless surface, laying down. 1/2 kx squared is the total energy that you put into the system. And it's going to come out. How's it going to come out? Well, it's going to come out with both of these guys going the same speed until they separate. They'll separate right when it goes through the equilibrium position. Right when it goes x distance after the compression. That's it. Why don't you multiply by 2 on each side of the equation, divide by the sum, m1 plus m2, and v squared equals k over the quantity m1 plus m2. Yeah, we're saying right when he gets here, I mean, he flew off. The drawing's not the best. It's almost like they're still together right when he gets here, and right at that instant, the guy takes off. So this drawing's not the best, but maybe it's okay because you want to show that it's taking off. In reality, right when it comes here, they're both going at the same speed right through the equilibrium position. They're both going at the same speed. Really? Well, when the guy flies off, that's an interesting dynamic in its own right, isn't it? You got this. It's pretty important stuff. So what we got here, you got this. Let's do the math. I mean, the math is going to go. Take the square root of both sides. Times x. Let's see. That's 4.5. Let's see what we got here, guys. M1 is 4.5. M2 is 3. 4.5 plus 3 is 7.5. K is 225. Right? So 7.5, and K is 225, right? 7.5 goes into 7.5 goes into 225. 7.5 is really 75 over 10. 75 goes into 225 3 times. And then the 10 flips over, divided by 10. So it should be 30. It's going to be, this is all going to be the square root of 30 times x. And that'll give you v. That's all it is. At the end of the day, let's just make sure that's on the mark. Yeah, it sure is. Sure is. 225 divided by this sum, which is 7.5. 225 divided by 7.5 is 30. The square root of 30 times x. X is 0.15 meters. 0.15 meters times the square root of 30 will give you V. V is going to, you plug in the numbers, just go for it. Deal with the calculator as we need to deal with it. There it is. That's the speed of both of these guys going through the equilibrium position. And then he takes off. Bam, he goes. You got him, you know, right when you go through the equilibrium position, what's going to happen? So that's how it's coming out that way. V1 max, V2, they're both going at that speed. Here's the problem, guys. Right here, they're both going at that maximum speed. That maximum speed which both of them have attained, mass M1 and mass M1 and mass M2. Mass M1 and M2, they're both going 0.822 meters per second. Then what happens is the spring starts kicking into gear onto M1. M2's not affected. M2 takes off. M2 takes off at 0.822. The blocks were in contact when the maximum speed was reached. So Vmax is 0.822 meters per second to the right. So when passing the other way, kind of a neat scenario here. When it passes the other, because the other guy's not coming back. Let's say it's an infinitely long track. It's an infinitely long experimental chamber, whatever lab in which we're working. That goes, man. He's going to go, and he's going he's going at 0.822 meters per second forever. Things as big as the state of Wisconsin. It's as big as the state of New York. Whatever. It's just going. Yeah, that's fine. This guy's going to get caught. And when he gets caught, he's going to lose all his kinetic energy. What is all his kinetic energy? It's 1/2 M1 times 0.822 squared. All that kinetic energy is going to go into potential energy. And then what happens? Well, this guy's long gone. This guy's long gone that way to the right. This guy will go to the max and he'll come back. And when he comes back, coming through, he hits 0.822 again. So V1 max to the right, V1 max when it was going to the right was 0.822 meters per second to the right. Negative V1 max is negative 0.822 meters per second. That means when it's going to the left, coming back. Either way, this guy's taking off forever at 0.822 meters per second. He ain't going to slow down until he hits something. This guy will hit his max here as well, but he's going to get slowed down by the spring. And then the spring is going to bring him back the other way. Here he's plus, here he's negative. The magnitude at the equilibrium point. At the equilibrium point. And that's basically what they were trying to say, guys. Let me look at it. Yeah, that's right. That is correct. Okay. 80 and 81. Okay, guys, 80 and 81. Let's see how that plays out. They are similar. There's a different nuance to each one, which makes it rather interesting. But let's see what we got here. For problem number 80. For problem number 80, two springs with spring constants K1 and K2 are connected to a block of mass M on a frictionless horizontal table. The block is extended a distance x from equilibrium and released from rest. Show that the block executes simple harmonic motion with a period given by this very interesting equation. Let me go to 81. Maybe we can kill two birds with one stone on this one. This shows, there's a figure that shows two springs, and they're connected to a block of mass M, and there's something else going on here. So there's two drawings I'm going to make here. Let me just see. Let me just kind of be careful how I do this. I don't want to run into issues of how much time I got, but I think we're okay. I think I can do this pretty straightforward. Okay, this should be straight. Yeah, there's a number of ways this can be looked at. I think the drawing will help everybody. If you've got the Katz book, you'll know exactly what I'm talking about when you read problems 80 and 81. And when I draw it, hopefully it's a pretty decent drawing. Those in the Survey book that are taking non-calc based treatment of what I'm doing here, the non-calc based treatment, this can still be done. Done quite well. So let me draw this out. You just need to get a hold of the text to be able to read some of this stuff. And that's very oftentimes in this day and age not very difficult to do. So should be able to do that. So if you get the Survey book, just find the problems, and I'll explain as much as I can while I'm doing this. You may not even need it if I show you enough. And those with the Katz book, you just read the problem as well and look at what I'm doing. So there's two problems here, guys. They're showing two systems that involve springs. The first system is a system that's got two springs attached one to the other. You know, one of the springs is here, and the other spring is right next to it, attached to it. The other one, and they've got it somewhere else, so you're kind of forced to kind of look at it or try to find it. And for the life of me, I can't find it. Let me just see here, guys. And there's the other one. Okay, they got it in the actual problem there. Okay, let's do this. Let's look at this. Let me try to solve these two. 80 and 81. Let's give us a little bit of room here. Let me see what I can do about it. Very fascinating problem. Both are very interesting problems. I think it's good to look at them almost simultaneously. Okay, so 80 and 81 are what we're going to do, and then we're going to be done with the Chapter 16 discussion for Physics 209, Calc-Based Physics. And again, always, whenever you're encountering the problems I'm showing you guys, if I make them something that I would suggest seeing or make them optional to see, and they're in a different book, getting a hold of the book is not a bad idea. I often try not to put people in that situation. I try to print out the problems, but other times that's simply not something that's very easily done. So it's easier for you to get a hold of the book sometimes. So let's see what we have here. Let me write. Okay, guys, so for 80, they want you to find an equivalent spring system for this situation. They want you to actually prove something. It's a pretty fascinating problem in its own right. Frictionless environment again. The mass to which it's attached is mass M, whatever that may happen to be. There is a spring, and then there's another spring, one of the springs has spring constant K1, and the other spring has spring constant K2. They're attached right there. And they're going to make this thing oscillate, and they're going to say it's simple harmonic motion when it does. And they want you to prove the period is what, this is easier shown than it is talked about too much, guys. So let me see what I can do here. The other one, for problem 81, they're saying, okay, let's not attach it like that. Let's attach it like this. That's got spring constant K1, and this has got spring constant K2. Let's say they're the same springs as they are over there to your far left. But that's what they're saying here, guys. So there's two scenarios here, guys. Let me go one by one on this. Let's see what we can do. At equilibrium, we can say this according to Newton's third law. Does everybody agree that if I pull, they're saying they're going to pull this thing out as far as you can pull this thing out, I guess you could say. And we're going to say x equals x1 plus x2. What does that mean? At equilibrium, there's going to be a total stretch. I can, right here, let's say right here, right now, for problem number 80, there is no stretch on this thing. But when you pull this thing out, take this guy and pull him out, I don't know how I want to say this. If you pull him out to here, you pulled him out a total amount x to get him out to here. Got him out to here, and then, that's all this stuff, You got him out to here, you let him go, and then simple harmonic motion is going to happen. I'm just saying this. If the total amount of pullout is x, then the amount that this guy was stretched is x1, and the amount that this guy was stretched is x2. This guy, K1, got stretched x1 amount. This guy, K2, got stretched x2 amount. So K1 got stretched x1 amount. K2 got stretched x2 amount. Together they give you that. Okay. We also know once you've stretched them out, that guy in the middle ain't moving. This guy's pulling. One guy's pulling with K1 x1, and the other one's pulling with K2 x2. And you know what? The middle guy ain't moving. If the flag ain't moving in the tug of war, then you're pulling as hard as I'm pulling. K1, X1, got to be the same as K2, X2 if that middle guy ain't moving. How do I know it's not moving? Because I pulled him out here and I held him before I released. I held it before I released. So what does that mean? Well, if you divide by K2 on each side and divide by X1 on each side, K1 over K2, K1 over K2 equals X2 over X1. What does that mean? If you multiply by X1 on each side, X2 equals K1 over K2 times X1. True. Therefore, if X2 is this, why don't you put it right here? X equals X1 plus x2, and x2 is k1 over k2. Very important. Very important, but I can't find my chalk. Okay, here we go. Very important conclusion. At least a semi-conclusion. We're not there yet. Okay. We're looking at it. And let's see what we can say here. Whole bunch of things you can say here. I'll tell you what. Can you say this? Can you say that x1 is the same as any number divided by itself, which is the same as 1, times x1? And this is k1, k2, x1. I'm going to purposely try to keep these letters active somehow. Is this right here the same as 1 right here? A 1 straight down, 1 times x1. Is anything divided by itself 1? k2 over k2, k2 over k2, x1, plus k1 over k2, x1, is going to equal, what does that equal? We end up getting x equals, let's get these together, guys. Let's figure out what this is. What it is K2 on the bottom, K2 plus K1. K2 plus K1 is the same as K1 plus K2 times X1. Yeah, I can, guys, there's an X1 right here. You can factor an x1 out of there. And that's equal to x. You add these together, okay? You simplify all this and you get that. Okay. Let's go further. The force F, look, I mean, both of these guys are equal to a force F. They both are equal to force F. Can you solve for x1 in terms of the force? Basically, you're saying k1 x1 equals k2 x2, and they both equal a force F. x1 is F over K1. Okay. X1 is F over K1. K1, K2, K1 plus K2 over K2. This guy is F over K1. Now what's going on? Well, multiply K1 and K2, just put them together, and you get X is equal to K1, K2. Hey, man, just multiply the two fractions if push comes to shove. Leave the F alone, and you got K2 times K1, which is K1, K2. K2 times K1 was... Now, wait a minute. What's going on here? Solve for F. Why don't you multiply... Solve for F. multiply each side of the equation by the reciprocal of this fraction. F equals wait a minute. Okay, forgive me. There's this up here. That's 81. Ignore 81 right now, guys. It's on there, but you see how we're proceeding with this problem. Guys, what's going on here? That's the equivalent. I'll make a long story short. Guys, is there... Okay, please forgive that up there. Ignore 81 for now, guys. It's not... 81 is not in the game yet. And I'll erase all this stuff. So ignore that for now. We're dealing with that way down there. So all this right here is coming to right there. There is the effective spring constant. The effective spring constant is K1, K2 over K1. The effective spring constant is K1, K2 over K1, K2 over the quantity K1 plus K2. K1 times K2 over the quantity K1 plus K2. Is that true? Sure looks like it. That looks like a K. That looks like an X. And that looks like an F. F equals KX. F equals K1, K2. As bizarre as it may look, this is square units of the spring constant. This is linear units of the spring constant. When you divide them, you get linear units of the spring constant. That's the K. That K right there is this times X. So K effective, the effective spring constant, is this. If they're set up that way. If they're set up that way. Okay. Yeah. Great. So now what? Well, okay, well, we did a lot of stuff to get to that. How are you going to get the period? T, capital T. Guys, do we know as a general rule, if there's simple harmonic motion in a spring system, omega is K, the angular frequency omega, is equal to the square root of the ratio K over M. Okay. Is omega the same as 2 pi over capital T? Sure is. Why don't you get the reciprocal of both? Why don't you multiply by 2 pi on each side? Yeah. Why don't you put the K here The K effective is just the new K. And it's, you know, K1, K2 over the sum K1 plus K2. We'll put that here on the bottom, K1, K2 over the sum of K1 plus K2. You've got this fraction. When you take a number divided by a fraction, you get the number multiplied by the reciprocal of the fraction. It becomes M, the K1 plus K2, like that, comes like that, and then on the bottom, that's it. For this guy, that's it. How'd that happen? Because the K, which is K effective right here, ignore this, we haven't activated that guy yet. That guy right there is T equals 2 pi over the square root of, and then here we go, K1, K2 over K1 plus K2. Dividing by this fraction flips the fraction upside down. Dividing by this fraction flips the bottom part of the fraction up to here, keeps this guy down there, and that's why we're getting this. Remember, they said it was simple harmonic motion, guys. Simple harmonic motion means, simple harmonic motion for a spring means the effective spring constant, let's call it K, divided by the mass M, that ratio square rooted gives you omega. Well, what's omega? Omega is 2 pi f, or equivalently speaking, it's 2 pi divided by capital T. 2 pi divided by capital T is the square root of K over M. I want to solve for capital T. Let's get the reciprocal of both sides and get to here. Then multiply by 2 pi, you get to here. Then plug in the K, this K right here, plug in the K, this whole mess right here, which is now the K, the effective K. K is equal to K effective. It's all that. Plug K effective into here. That's what I did right here. That flips over and you get this. Here is your answer at the end of all that. Okay? I don't want to write it like that too much, but okay. You guys know where I'm coming from. There it is. That's how it looks. That's how it looks. They're asking for a similar argument. Now, what really sprung the whole thing into action, you guys? What sprung the whole thing into action was when you stretch this guy by an amount X in total. When you stretched the spring, when you stretched this combination of springs, you took these two springs, which are one master spring, I guess, right? They're one master spring. When you stretched this spring conglomeration, when you stretched this spring system by an amount X, there was X sub 1 stretch on this guy, X sub 2 stretch on this guy. That total X is X sub 1 plus X sub 2. When you stretched it that amount X in simple harmonic motion, you look into it. Another thing that came into play is once you did the whole stretch, that guy right here, that ain't moving. If that ain't moving, the pull of this guy and the pull of that guy are at a dead heat. You got K1 X1 equals K2 X2. K1x1 equals K2x2. And that was kind of the beginning of where you're going to go to get this problem to happen. Okay? That's 80. That's 80. 81, see what we can say here. So 81's maybe a little bit easier in some way. This one's a little different dynamic. If you stretch one of them, you're compressing the other. It's kind of a double whammy on that one. The other ones weren't really quite the double whammy because they were kind of connected to each other, and somehow it was just, you know, it kind of one equivalent spring. We're going to get one equivalent spring here too, but this is a little different dynamic. If you take this guy and stretch them from here to here, let's say, a distance x, you stretch it a distance x, this guy right here is going to pull him. If you stretch this guy that way, a distance x, this guy's going to try to pull him back, and this guy's going to try to push him back. They're both, one's pulling, one's pushing, but they're I guess it's like me saying, hey, I've got to pull this very, very heavy object across the floor. I tied up the rope and I'm pulling the very heavy object. You're on the other end of the object and you are pushing in the same direction in which I'm pulling. That's what it means. You're helping me. What's the total force? It's the force I'm putting on to go to your right. I'm pulling to your right, and the other person is pushing to your right. I'm F1 in force. The other person's F2 in force. F1 plus F2 is the total force. That's the key. That's the key on that one. So what's going on here? K is going to be K effective. K equals K effective. I used K last time, and then I kind of went back to K effective. But K is easier. It's less clutter, I guess. K is equal to K effective. What's going on here? I'm going to make the statement that the total force this guy, the total force this guy experiences is the following. The total force he experiences is the following. This K2 guy pushes him because this K2 guy got compressed X amount. The K1 guy got stretched X amount. How about K2 plus K1? K2's pushing back because he was compressed X amount. X amount compression time. Remember, it's an ideal spring. When it's compressed, it'll push at you the same way it would pull at you if it's an equal distance of displacement. If I displaced it X amount, either in compression or stretching, if it's X amount of a stretch or X amount of a compression, it's the same force. It'll push with K1x or it'll pull with K1x. Or it'll pull with K2x or push with K2x. If you displace this thing by X amount in compression, then K times X, then let's talk about K1. K1, if you compress it X amount, K1 times X, X amount compression, K1 times X is the amount of push to your left. If you stretch it X amount, it'll try to pull you to the left. So this is I'm sorry, K2, whatever one. This is K2. So if you compress it X amount, K2X is the amount of pushback you get. While you've compressed it X amount, you've stretched this guy X amount. His pulling you, this guy's going to, the K1 spring is going to pull you K1 X amount to the left. The K2 spring is going to push you also to the left with K2 X amount. That's what I wrote here. F equals K1 plus K2 times X. A little different dynamic here. This guy's the effective spring constant. He looks like K times X, guys, to give you F. Therefore, K equals K1 plus K2. What's going on here? Same thing that went on last time. Kind of, sort of the same thing. Omega is K over M. Omega is 2 pi F equals the square root of K over M. Didn't say that explicitly last time, or he didn't write it, but there it is. Well, let's write this. This is easier to write. 2 pi over capital T is the square root of K over M. If two things are equal, their reciprocals are equal. Multiply by 2 pi, you know where I'm going. Multiply by 2 pi on each side. Here's M. The other, the K effective, K1 plus K2. And there's your answer. There's your answer. So a lot can be said. I mean, there's a whole lot can be said here, guys. The other guy, as we said, was something different. It's a different dynamic. How that plays out, okay? So for this system, you get this. And that's 81. All right, it's completely in the notes in that same manner, you guys. The big thing here is it gets help right off the bat. So to me, you know, just looking at this thing, if you were comparing the two dynamics, you know, for 80 and 81, here's 80, here's 81. The omega is this. Now, you keep that in mind, it's for both. Omega is this. And what's that going to be? Omega would be the angular speed. Very close to frequency. I mean, it's 2 pi f. The frequency would be omega divided by 2 pi. So it's just, they're directly proportional. A large omega means a large f. Omega is just 2 pi times bigger than every f. But a large f means large omega, a small f means small omega. Omega is just 2 pi times bigger than f. Because you're not talking about a whole cycle, you're talking about radians per second. Whereas f talks about all 2 pi radians every cycle. Whereas per radian, it's a bigger number because radians, you cover a radian faster than you cover a revolution. 2 pi times faster. So they're saying something like that. For 80, and for this guy, I mean, the way you would do it, if you just left it here as omega, the K for the 81 was K1 plus K2 over M squared. The other guy is, I have to kind of look at it. K1, K2. This is a little extra. They didn't ask us for this. M, K1 plus K2. It's a different dynamic. Notice the units are the same. M is on the bottom. This right here is K squared units. This is just K. It's just going to be K units. This is going to be K units straight out. And you know, it's an interesting matter which one's bigger for a given situation. What you got here this one should be a bigger number. The reason for that is you wouldn't, this has got to be smaller than that because this right here arose from, well, there's a whole bunch you could argue on this one, guys. You really could on this one. K1 squared, K2 squared, 2K. Yeah, this one would be bigger because this one right here, you guys, watch this. Usually it'd be bigger. I could put an M K1 plus K2 M K1 plus K2 right here. Let me put a K1 plus K2 on the bottom here. Let me multiply here on top. Well, this is K1 plus K2 squared. Yeah, wait a minute, man. K1's got size, K2's got size. Great. K1 plus K2 has more size than K1 or K2. And you wrote it down twice. In other words, let's compare the two. This is a K1. Let's compare the tops. K1, K2. The other one is K1 plus K2 and K1 plus K2. Wait a minute. Let's talk. You agree that K1 plus... These aren't negative numbers ever. There's no negative numbers here, guys. And there's no zeros here. For our purposes. No zeros here, no negative numbers. If there's no negative... If the numbers are always greater than 0, they're positive real numbers. Positive real number plus positive real number is bigger than either one of these. There's no zeros here. K1's not 0, K2's not 0, and there's no negatives. These are positive real numbers. A positive real number plus a positive real number gives you an answer that's bigger than either one of these positive real numbers. K1 plus K2 is bigger than K1. K1 plus K2 is bigger than K2. This omega, you know, I don't know what you want to call it, omega 81, you know, call this guy omega 81, call the other guy omega 82. Omega, you know, omega 81 for this guy and omega 80 from problem 81 for problem, and the other guy's this. That's this guy, and the other guy is this, K1, K2 over M K1 plus K2. This guy is smaller. So let me see here. Again, these problems were done about 10 minutes ago, guys. I just want to kind of tell you. Omega 81 is bigger than omega 80. Why is that? Because the square root of K1 plus K2 times K1 plus K2, over M K1 K2 that's bigger than just this guy, a K1 times a K2. A K1 times a K2, the K1 is smaller than one of these, is smaller than K1 plus K2, and the K2 is smaller than K1 plus K2. This is really K1 plus K2 times K1 plus K2. This is bigger than that, for sure. And this is bigger than that. And the bottoms are the same, so nobody changes. The bottoms don't change. It's always bigger. 80 is bigger, 80 is bigger than 81. I'm sorry, 81 is going to be bigger, so it's going to be this way. The answer there. Well, why am I making a big deal out of this? You understand I can do a shorthand here and call the quantity K1 plus K2 times the quantity K1 plus K2. I can call it the quantity K1 plus K2 squared. Right, and I can go even more shorthand. The quantity K1 plus K2 goes into the quantity K1 plus K2 squared, K1 plus K2 times. And that's what that was the K1, the K1 plus K, K1 plus K2 times. We actually got the answer. And that's K1 plus K2 times. This quantity, K1, the quantity K1 plus K2 goes into the quantity K1 plus K2 squared, the quantity K1 plus K2 times. It's that one. Well, that's important. Why is 81 bigger than 80? Because it's a more violent restoration, so to speak. This guy, this setup involves a push and a pull in teamwork simultaneously on the mass. One of them, this guy, you stretch this guy and he's pulling him right back. You compress this guy and he's pushing him right back. The push and the pull are in tandem with one another, so it's a more forceful action. If it's a more forceful action, K will be bigger. There's more force. If there's more force, you need a bigger K for there to be more force. If K is bigger, well, here we go. If the mass stays the same, but K gets bigger, if the mass stays the same, but K gets bigger, then the square root of K over M is a bigger number. The effective K is bigger because there's teamwork here. This guy, having been stretched, is pulling him right back to the left. This guy, having been compressed to the right, is also pushing him. Is also trying to... This guy, having been stretched to the right, is pulling him right back to the left. This guy, having been compressed to the right, is pushing him right back to the left. They're both working together, pushing him back to your left. It is a more forceful action. A more forceful action means the effective spring constant must be bigger. If the effective spring constant must be bigger, then K is bigger than the other scenario when they were piggybacked to one another, when one was tied to the other. Here they're not tied to each other. They're at opposite ends, but they're working together better than the other guys are working together. This guy will oscillate. They'll both oscillate with simple harmonic motion. The problem in problem 80 and the problem in problem 81. The scenarios in problems 80 and 81 both oscillate with simple harmonic motion. There is just more frequency. There's more energy. Could say there's more energy in the system as well. If the omega's like that, if I extend it the same way, there's more. What's kinetic energy? 1/2 mass times velocity squared. Well, the velocity is going to be omega times a for the maximum velocity. If I stretch them the same amount, then omega times a is the formula, but if this omega is bigger, it's going to be a bigger maximum velocity going right through the middle. A bigger maximum velocity going through the middle means more energy in the system. If you think you're going to pull them over in one direction, X amount of units, for problem 80, you needed a particular amount of work to get done for you to do it. For problem 81, you will have to do more work to move it the same amount as you did in problem 80. But once you did it, there's more energy in the system. It will have a greater maximum speed, more energy in the system, and its oscillation will be more rapid. Omega and F will be more frequent. The frequency will be greater for problem 81. If omega is greater, the frequency is greater. If the frequency, you have a more, it's whipping back and forth faster, so to speak. If omega is greater, then the frequency F is greater. If the frequency F is greater, the period for one whole cycle is less. So 81 has a smaller period than 80 does, which is equivalent to saying that 81 has a greater frequency than 80 does. 81 has a smaller period than 80 does. Problems 80 and 81 now. The scenario in problem 81 has a smaller period than the scenario in problem 80. Yeah, that means that it oscillates with greater frequency in problem 81 than it does in 80. And there's more kinetic energy at the maximum for problem 81 than there is for 80 because it took more work for you to stretch. It may take you, for problem 80, it may take you 5 joules to stretch this thing X amount. In 81, it may take you 10 joules. It's going to take you more work. It's more work. It's a tougher spring. If it's a tougher spring, it takes more work to stretch it. To stretch it the same amount, it takes more work if it's a stiffer spring. If it's a stronger spring, it takes more work to stretch the same amount. They both do simple harmonic motion. All right, you guys. Thank you for your time. We'll talk again soon. Take care.